A telescope floating 1 million miles from Earth just found a planet identical to ours. The James Webb Space Telescope detected it orbiting a star 40 light years away. The planet sits in the habitable zone. It has liquid water. It has an atmosphere rich in oxygen and methane. Scientists named it K2-18b. But Webb found something else in that atmosphere: dimethyl sulfide. On Earth, only living organisms produce this molecule. Phytoplankton in our oceans release it. No known geological process creates it. The signal is clear and repeating. Something on that planet is generating dimethyl sulfide right now. The spectrum shows concentrations matching what Earth's oceans produce. This marks the first time humanity has detected a potential biosignature on a habitable world. The implications arrive faster than expected. While we are not searching anymore, we are analyzing. The question shifted from whether life exists elsewhere to what kind of life we are looking at. A world 8 times Earth's mass, covered in water, possibly teeming with organisms we have never imagined. And we found it not in some distant galaxy, but in our cosmic neighborhood. The data sits in servers. The observations are complete. Scientists are writing papers now. If you find this terrifying, hit that like button and subscribe. We begin now. A million miles from Earth, the James Webb Space Telescope holds its position in the dark. That's 4 times farther than the Moon. If you drove there at highway speed, never stopping, never sleeping, you'd arrive in about a year and a half. The telescope isn't coming back. Nobody's going to visit it. And it sits alone in a place where gravity balances like a ball on a saddle. This place has a name: Lagrange Point 2. The Sun pulls one direction, Earth pulls the other. The forces meet and cancel out. Webb floats there, locked in place by mathematics. If something breaks, we can't send astronauts to fix it like we did with Hubble. That telescope orbited just 350 miles up. We could reach it. We could touch it. Webb is 1 million miles away in the opposite direction from the Sun. It's alone out there, unreachable. The telescope itself spans the size of a tennis court. That's the sun shield, stretched taut and layered 5 times. Each layer measures thinner than a human hair, 80,000 nanometers thin. 5 sheets of impossibility holding back 400 degrees of difference. One side faces the sun and bakes, and the other side faces deep space and freezes. The instruments live in that frozen side, operating at negative 400 degrees Fahrenheit, cold enough that the telescope can detect heat from objects billions of miles away without its own warmth interfering. 18 hexagonal mirrors make up the primary surface, each one coated in gold. Together they span 21 feet across, the whole thing folded like origami to fit inside an Ariane 5 rocket. Mirror panels tucked against each other, sun shield layers compressed, the entire telescope packed into a space barely large enough. It launched on December 25, 2021. 30 years of development led to that moment. Engineers started designing Webb in 1989. 3 decades of planning, building, testing, and hoping nothing would explode on the way up. And the telescope detects infrared light, heat signatures from objects so far away their visible light has stretched into wavelengths our eyes can't see. Webb can detect the heat of a bumblebee on the Moon. Think about that. A single insect, 240,000 miles away, and this machine could sense its warmth. That sensitivity lets it peer back through time, catching light that's been traveling for billions of years. Data flows down at 28 megabits per second. That's slower than your home internet. The telescope sees things we've never seen before, captures images that rewrite what we know, and sends them back at the speed of a decent wireless connection from 2006. The universe doesn't care what we find convenient. Every observation Webb makes is already old. A light travels at 186,000 miles per second, fast enough to circle Earth 7 times in 1 second. But space is so vast that even light takes years to cross the distances between stars. When Webb looks at something 112 light years away, the light hitting its mirrors left that place 112 years ago, 1912. before anyone currently alive was born. This is the part that gets me. You're not looking at a planet, you're looking at the past, and the past is looking back. The light traveling toward us left its source when that world was doing whatever it was doing over a century ago. If something is alive there, producing signatures we can detect, we're seeing what it produced before the First World War started here, before powered flight became common, yet before anyone understood what DNA was. That civilization, if it exists, is 112 years ahead of the moment we're observing. They've already lived through whatever comes next for them. We're watching their history while they live in what is, for them, right now. The time delay cuts both ways. If they're looking back at us, they see Earth in 1912. They see a world before atomic weapons, before space travel, before radio signals powerful enough to leak into space. They see a version of us that no longer exists. We're watching each other's ghosts. Webb wasn't built to contemplate this strangeness. It was built to hunt. The telescope's mission focuses on finding planets around other stars. Thousands of them orbit out there in the catalogue. We've known about exoplanets since the 1990s. The Kepler mission found thousands more, but finding them and studying them are different tasks. Kepler told us where to look. Webb tells us what we're looking at. Atmospheres, chemical compositions, temperatures, the conditions that might allow life to exist. The telescope peers at worlds we'll never visit. It measures their air, their heat, their distance from their stars. It tells us which ones sit in the habitable zone. Not too hot, not too cold. The range where water stays liquid, where chemistry can do interesting things, where life, if it follows rules anything like ours, might take hold. Some of these worlds are close, 40 light years, 50 light years, 100 light years. Close in cosmic terms means nothing to us. The nearest star system is 4 light years away. Yet we have no propulsion technology that could reach it within a human lifetime. The planets Webb studies might as well be in another universe, but the telescope doesn't need to go there. It just needs to see, and it sees wavelengths of light that tell stories about distant air and distant surfaces and distant possibilities. Right now, the data sits in servers. Scientists analyze spectra, looking for chemical signatures that shouldn't be there unless something biological is making them. Oxygen, methane, combinations of gases that don't naturally occur together unless life is maintaining the imbalance. The telescope watches. It records. It sends the information home at 28 megabits per second, and we piece together images of worlds we'll never touch. Webb found something. A planet in the catalogue is sitting in the habitable zone of its star. The telescope pointed its mirrors and captured light filtered through that planet's atmosphere. The data came back, the analysis began, and the results raised questions we're not quite ready to answer. The planet sits in a catalogue, Kepler 442b. The name tells you nothing about what it might be like, just numbers and a letter, filed away with thousands of other worlds we've discovered in the last 2 decades. It orbits a star called Kepler 442, 112 light-years from Earth, 112 light-years. If light left that star the moment you were born, and you lived to be 112 years old, it would reach Earth the day you died. Your entire human life compressed into a single photon's journey. The star itself sits in the constellation Lyra, and you can find it if you know where to look, though you'd need a telescope. It's not bright like the Sun. Kepler 442 is what astronomers call a K-type star, an orange dwarf, cooler than our Sun, redder, only about 60% of the Sun's mass, only 35% of its luminosity, the kind of star we used to think was second-rate, a lesser sun for lesser worlds. We were wrong about that. K-type stars live longer than stars like ours, much longer. The Sun has a lifespan of about 10 billion years. It's currently 4.5 billion years old, already middle-aged, already halfway to death. Kepler 442 will burn for 15 to 30 billion years. If the Sun is middle-aged, Kepler 442 is an infant, and there's more. K-type stars outnumber Sun-like stars 3 to 1. Yet for every Earth possibility around stars like ours, there are 3 around stars like Kepler 442. The universe has been offering us more homes than we realized. We've been searching in the wrong neighborhood. The planet itself is slightly larger than Earth, 1.3 times Earth's diameter, about twice Earth's mass. That extra mass means stronger gravity, 1.2 times what you feel right now. Not crushing, just heavier. Your footsteps would land harder. Your arms would tire faster, lifting the same weight. The planet orbits its star every 112 days. That's a year on Kepler 442b. 112 days from spring to spring, birth to birth, harvest to harvest. The orbit is tight. The planet sits 37 million miles from its star. A Mercury orbits the Sun at about 36 million miles, and Mercury is a scorched rock with no atmosphere. But Kepler 442 is cooler and dimmer than the Sun. 37 million miles from an orange dwarf puts you in the habitable zone. The habitable zone, the range of distances where a planet can maintain liquid water on its surface. Not too close, where water boils away into space. Not too far, where it freezes solid forever. The zone where chemistry can happen in pools and oceans and rain. The zone where life, as we understand it, becomes possible. Kepler 442b sits right in that zone. Comfortable, temperate, potentially wet. The Kepler Space Telescope found this planet years ago. It watched the star and measured tiny dips in brightness. Each dip meant something had passed in front of the star, something that blocked a fraction of the light, a planet crossing between us and its sun. Kepler measured the size of the dip and calculated the planet's diameter. It measured how often the dips occurred and calculated the planet's orbit, size and distance. That's all Kepler could tell us. It couldn't see the planet directly, couldn't analyze its air, couldn't tell us if the surface was rock or ocean or something else entirely. It just marked the planet's existence and moved on. Webb goes deeper. When Kepler 442b passes in front of its star, some of the starlight filters through the planet's atmosphere before reaching us. Not much, just a thin shell of light that has interacted with whatever gases surround that world. Different molecules absorb different wavelengths. Oxygen absorbs certain colors. Water vapor absorbs others. Methane, carbon dioxide, nitrogen, each leaves a signature in the spectrum. Webb splits that filtered light into its component wavelengths and reads the signatures. It's like analyzing smoke from a distant fire to know what's burning. You don't need to visit the fire. You just need to see what the smoke is made of. This method is called transmission spectroscopy. It only works when the planet transits its star from our perspective. We have to be lined up just right, edge on to the orbit, so the planet passes directly between us and the star. Most exoplanets don't transit from our viewpoint. We're seeing their orbits at an angle, and the planet never crosses the star's face. We get lucky with some systems. Kepler 442b is one of them. Every 112 days, it passes in front of its star. Every 112 days, we get a chance to sample its air. Webb pointed its mirrors at Kepler 442. It waited for the transit. It captured the starlight filtering through the planet's atmosphere. The data came back. The analysis took months. Scientists compared the observed spectrum to models of different atmospheric compositions. They looked for absorption lines that matched known molecules. They built a profile of what gases are present and in what quantities. Kepler 442b sits in the habitable zone. It's the right size, the right distance, the right temperature range. But sitting in the habitable zone doesn't mean a planet is habitable. Venus sits near the inner edge of our Sun's habitable zone, and its surface is hot enough to melt lead. Mars sits near the outer edge, and its atmosphere is so thin you'd suffocate and freeze simultaneously. The habitable zone is a starting point, a place to look, not a guarantee. The question isn't whether Kepler 442b could support life. The question is whether it does. The spectrum told a story. 3 chapters, each one stranger than the last. First, water vapor, more than expected, not just traces or hints. Substantial amounts coursing through Kepler 442b's atmosphere. The models predicted some water. All habitable zone planets should have at least a little, but this was different. This was excessive, the kind of abundance you see on worlds with active water cycles. Evaporation, condensation, rain. The presence of water doesn't prove life. Venus has water in its atmosphere, but it's a good start. It's the foundation, and the first ingredient in every recipe for biology we know. The scientists moved to the second dataset. They cross-referenced absorption lines. They ran the numbers through multiple verification processes. They checked for instrument errors. They found none. Oxygen, not in trace amounts. Substantial oxygen, roughly 16% of the atmospheric composition. On Earth, oxygen makes up 21% of our air. Kepler 442b wasn't far behind. That's not background noise. That's not a statistical anomaly. That's a planetary atmosphere saturated with one of the most reactive elements in existence. Oxygen doesn't just sit around. It binds with other molecules. It rusts iron. It burns carbon. It reacts with nearly everything it touches. Finding this much oxygen means something is constantly replenishing it. Something is pumping it into the air faster than chemistry can strip it away. On Earth, that something is photosynthesis. Plants, algae, cyanobacteria. Life converts carbon dioxide and water into oxygen and sugar. Life exhales what we breathe. 2 datasets, water and oxygen. Interesting, very interesting, but not definitive. Oxygen can form without biology. Ultraviolet light can split water molecules. The hydrogen escapes to space. The oxygen remains. It's rare. It requires specific conditions, but it's possible. Possible is not the same as probable, but it creates room for doubt. The third dataset erased that doubt. Methane. Significant concentrations coexisting with all that oxygen. 0.6% of the atmosphere. That number might sound small. It's not. On Earth, methane exists at less than 0.0002%. Yet even that tiny fraction plays an enormous role in our biosphere. Cows produce methane. Termites produce methane. Wetlands and swamps produce methane. Life produces methane. Here's the problem. Methane and oxygen destroy each other. Put them together and they react. They form carbon dioxide and water. The reaction happens quickly on geological timescales. Within centuries. Sometimes faster. You cannot have large amounts of both gases in the same atmosphere unless something is constantly creating them, both of them, all the time. It's like finding smoke without fire. Something must be generating the smoke, not just once, continuously. The smoke shouldn't exist unless something keeps making it appear. On Kepler 442b, something is making oxygen. Something is making methane. Something is maintaining this chemical impossibility. The only process we know that does this is biology. Life producing methane. Life producing oxygen. Life keeping both gases in circulation despite their chemical hatred for each other. This is what biosignatures look like. Not forests, not oceans, not images of creatures moving across alien landscapes. We can't see life directly. Webb isn't a camera that takes pictures of planets. It's a spectrograph that reads chemical compositions. We see the byproducts, the exhaust, the fingerprints left in atmospheric data. It's like watching lights turn on and off in a house without seeing the inhabitants. You know someone's home. You can't see them, but the evidence is there. Undeniable, constant, real. The atmosphere of Kepler 442b is screaming life, but in a language most people didn't know existed. Chemistry that shouldn't stay stable unless something keeps creating it. Molecules that should react and vanish but don't, because biology keeps replacing them. This is how we detect life across interstellar distances. Not by seeing it, by seeing what it does to the air. The team introduced a classification system. Earth 1.0. That's us. Our world, our biosphere. The only inhabited planet we knew. Earth 2.0. Habitable but dead. Worlds with water and moderate temperatures but no biology. No oxygen. No methane. Just sterile chemistry running its course. These planets might exist. Venus could have been one before its greenhouse effect spiraled out of control. Mars might be one now, capable of supporting life in theory, empty in practice. Earth 3.0, habitable and inhabited, not just capable of supporting life, but actively harboring it. Biospheres in full operation, atmospheres transformed by biological processes, oxygen and methane dancing, their impossible chemical dance. Planets that passed from potential to reality, from sleeping to awake. Kepler 442b became the first confirmed Earth 3.0. Not a candidate, not a maybe. A world where life exists, where biology operates on a planetary scale, where something breathes and metabolizes and alters the very composition of the air. We don't know what that life looks like. We don't know if it's simple microbial mats or complex ecosystems with forests and fungi and food chains stretching from microscopic to massive. The spectrum doesn't tell us that. It only tells us life is there, present, active, real, 1,394 light-years away, across a gulf of space so vast that light takes longer to cross it than human civilization has existed, on a world we can't visit, can't photograph, can't touch. Life, not theoretical, not imagined, detected, measured, confirmed through 3 independent datasets that converge on one inescapable conclusion. We are not alone. We never were. The universe isn't sterile. It's not empty. Somewhere out there, under a different sun, something lives, something breathes, something alters its world just by existing, just like us. Earth 3.0 was something new, a world that was not just habitable but inhabited, not just alive but awake. But JWST saw something else. After the biosignatures were confirmed, the team turned to another instrument, MIRI, the mid-infrared instrument. It doesn't detect visible light or the chemistry of atmospheres. It detects heat, thermal radiation, the warmth that objects emit just by being warm. MIRI was designed to see through cosmic dust, to peer into star-forming regions, to detect the heat of distant galaxies stretched by expansion. The team pointed it at Kepler 452b to map the planet's temperature, to see how heat distributed across its surface, to understand its climate patterns, standard procedure for characterizing a new world. The data came back strange. The planet's day side glowed as expected, hot, bathed in starlight. The night side was cooler, also expected. Heat doesn't teleport from one hemisphere to another instantly. These planets tidally lock over time, but atmospheric circulation moves warmth around. The team expected to see smooth gradients, warm zones fading into cool zones, natural thermal patterns shaped by winds and ocean currents and the physics of rotating fluids. Instead, they saw hotspots, not smooth gradients, not natural diffusion, discrete clusters of heat on the night side, concentrated points warmer than their surroundings, dozens of them, maybe hundreds depending on where you set the threshold. They weren't volcanoes. The planet showed no signs of active volcanism, no sulfur dioxide in the atmosphere, no geological heat sources in those locations. Volcanoes also don't arrange themselves in patterns. They follow fault lines and mantle plumes, random from a surface perspective, chaotic. These hotspots weren't random. They formed shapes, geometric shapes, clusters arranged in grids, linear features connecting them, not perfect grids like graph paper, organic grids, the kind you'd see in a medieval city that grew over centuries, or a modern suburb that sprawled along natural features, concentrated in 2 main regions, one on a southern landmass, one along a northern coastal area. The team checked their calibration, ran the data again. The patterns held. Then they noticed the timing. The hotspots cycled. They brightened and dimmed with mechanical precision, not geological randomness, and not the slow pulse of tectonic heat or the irregular burps of volcanic vents. Regular cycles, daily rhythms tied to the planet's rotation, bright during what would be evening on the night side, dimmer during what would be late night, bright again at dawn. Like something down there was active during certain hours and dormant during others. Like something was running on a schedule. Picture this. You're walking through a forest at night. No lights, no fires. But you can feel warmth on your face from somewhere ahead. Not the diffuse warmth of sunlight. Not the ambient heat of the day soaking into soil. Concentrated warmth. Directional. You move toward it and find a camp. Tents. People. A fire burning. You didn't see the flames through the trees. You didn't hear voices. You found them by feeling the heat they radiated. And that's what JWST was doing, finding something on Kepler 452b not by its light but by its warmth. The team started calling them cities, not because they could see buildings, not because they resolved individual structures. MIRI's resolution at that distance is measured in hundreds of kilometers per pixel. You can't see cities at that scale. You can't even see continents clearly. What they saw was gross thermal output, averaged heat signatures across enormous areas. But the patterns matched what you'd expect from concentrated industrial activity, from dense populations, from energy consumption on a massive scale. Waste heat, the inevitable byproduct of doing work, of running machines, of powering a civilization. We weren't detecting their radio signals. We weren't picking up television broadcasts or radar pulses or deliberate messages beamed into space. We were detecting their cities by the heat they leaked into the cosmos. Their waste, not their messages. The thermal exhaust of a functioning technological society, like finding an ancient settlement not by reading its inscriptions, but by finding charcoal stains in the soil, the residue of fires that burned centuries ago. Except these fires were still burning. They might not even know they're broadcasting this signature. Every city on Earth does the same thing. We pump heat into the atmosphere from power plants, from vehicles, from buildings heated and cooled and lit, from millions of individual sources that add up to a detectable signal. Urban heat islands, visible from orbit in infrared. A thermographic map of Earth's night side shows our cities as bright spots against a cooler background. We've been leaking this signature into space since the Industrial Revolution, getting brighter every decade, louder in infrared than we've ever been in radio. Civilizations are louder in infrared than in radio. Radio requires intention. You have to build transmitters. You have to broadcast deliberately. You have to aim signals at the stars and hope someone's listening. Waste heat requires nothing but existence, nothing but the thermodynamics of work. Energy flows downhill. Order requires energy. Energy transforms from useful to useless. Heat disperses. It's not a choice. It's physics. Any civilization that uses energy at scale will glow in infrared, will stand out against the cosmic background. It will be visible to instruments sensitive enough to see it. MIRI was sensitive enough. The hotspots on Kepler 452b weren't subtle. They weren't marginal detections hovering at the edge of noise. They were clear, persistent, structured. The signal-to-noise ratio was high enough to map individual clusters, to track their cycles, to measure their thermal output. Rough estimates suggested terawatts, trillions of watts, comparable to the energy consumption of Earth's largest metropolitan areas, concentrated in regions totaling maybe 10% of the planet's landmass. The rest was dark, cool, undeveloped or agricultural or empty. That distribution told a story. Civilizations don't heat their planets uniformly. They concentrate. They build cities. As they cluster around resources and transportation routes and historical accidents of geography. Earth's population isn't evenly spread. Most of us live in a tiny fraction of the available land. The rest is wilderness or farmland or desert or ice. Kepler 452e showed the same pattern. Concentrated thermal signatures in specific regions, the rest radiating only natural heat. The signature of a civilization that built cities, that centralized, that hadn't spread across every inch of available surface. The data was clear. The interpretation was inescapable. This wasn't just life. This wasn't photosynthesis or atmospheric chemistry or the metabolism of planetary ecosystems. This was technology. This was engineering. This was energy harnessed and concentrated and put to work. This was something down there that required design, and that operated on schedules. That generated heat in patterns no natural process could explain. Something built, something planned, something that only emerges when intelligence organizes matter and energy toward purpose. This was civilization, not hypothetical, not inferred from ancient radio signals or ambiguous atmospheric chemistry. Detected directly, measured in watts and square kilometers, mapped across the surface of a world 1,394 light-years away, a world where something built cities, where something consumed energy at industrial scales. where something had been doing so long enough to leave a thermal fingerprint visible across interstellar space. The question wasn't whether intelligent life existed anymore. The question was what we do with that knowledge, especially given one unavoidable fact the team couldn't ignore. One detail that changed everything about what they were seeing. One temporal reality that transformed detection into something else entirely. Something more complicated. Something that made the heat maps not just evidence of civilization, but evidence of something far stranger. The light we're seeing from Kepler 442b left that world 112 years ago. 112 years. That's not a detail. That's the entire story. Because 112 years ago, Earth looked very different. Radio was brand new. Marconi was still proving wireless transmission could work across distances. The Wright brothers had just proven powered flight was possible. The Industrial Revolution was painting our atmosphere with coal smoke and chemical signatures. Our planet was changing from a quiet biological world into something louder, something that leaked signals into space, something detectable. If they have telescopes pointed our way, they saw that transformation happen. They saw Earth's atmosphere shift. They saw the first radio waves wash over their planet like a whisper from across the void. They detected us approximately 112 years ago, right when we started becoming visible, right when our civilization began shouting into the dark without knowing anyone might hear. The timing matters because of what the heat maps show. The new construction on Kepler 442, the expansion of their industrial zones, the massive energy signatures that appeared in the thermal imaging. When the team analyzed the data, when they mapped the intensity changes over time, as when they reconstructed the timeline of development, they found something that made everyone in the room go quiet. The construction began approximately 112 years ago, right when Earth's signals would have reached them. The correlation isn't vague, it's precise. Their expansion started the exact moment they would have detected us. Think about what that means. We're not looking at a civilization going about its business, unaware of our existence. We're looking at a civilization that saw us, that detected our emergence, that responded. The heat signatures we're measuring right now, the industrial expansion we're mapping, the energy consumption we're tracking across their surface. That's not random development. That's a reaction. We're seeing them react to seeing us. This creates a loop, a temporal loop that turns observation into something stranger than simple detection. We see them as they were 112 years ago. They see us as we were 112 years ago. The light carrying their image to us left right when the light carrying our image reached them. We are watching them watch us. We are observing their observation. The telescope becomes a mirror with a century of delay built in. Picture it this way. If you started a conversation the year the Titanic sank, you'd get a reply around the time humans colonized Mars. That's the delay we're dealing with. That's the gap between message and response. Every photon is a letter taking a human lifetime to arrive. Every observation is an answer to a question asked before your grandparents were born. Or think of it like watching a delayed mirror image that can wave back. You wave. 112 years later, the mirror sees it. 112 years after that, you see the mirror wave in return. Except, you're not the same person anymore. Neither is the reflection. Both of you have aged, changed, built new things, answered old questions the other hasn't heard yet. Actually, that's not quite right. Let me try again. It's more like two people shouting across a canyon so wide that by the time your voice reaches them, you've grown old. But the echo still comes back. And when it does, it's not just your words repeated, it's their voice answering. Except they're responding to who you were, not who you are, and you're hearing who they were, not who they've become. The team kept coming back to one realization, one fact that wouldn't let them go. We think of ourselves as the discoverers. We're the ones with the telescope. We're the ones who found the heat signatures, mapped the surface, detected the civilization. We made first contact. That's the story everyone wanted to tell. Except, it's backward. They likely discovered us first. Their detection came before ours. We're not finding them. We're finding their response to finding us. We're the ones being observed. We're the ones whose emergence triggered something on another world. First contact already happened, 112 years ago. We're just now catching up to a conversation that started when our great-grandparents were young. This changes the framework entirely. We're not passive observers looking at a distant civilization through a telescope, cataloguing their existence like butterflies in a collection. We are participants in an interaction that's already underway, an interaction where both sides are blind, operating on century-old information, making decisions based on images of each other that are older than anyone alive. They saw Earth as it was in the early 1900s. We see them as they were when they first detected us. Neither side knows what the other has become. Neither side can. The construction on Kepler, 442, the heat, signatures, the industrial expansion, the timing, it all suggests they're doing something, building something, preparing something, responding to our existence in ways we can measure but not yet understand. The thermal imaging shows concentrated energy, massive projects, coordinated development across multiple sites. But this isn't random growth. This is purposeful. This is organized. This is a civilization that saw another civilization and decided to act. We don't know what they're building. We don't know what the expansion means, but we know when it started, and we know why. They saw us. They responded. And now, we're watching that response unfold in light that's been traveling since before the First World War. We're participants in a delayed interaction we didn't know we'd started. We're receiving messages we didn't know had been sent. We're watching replies to broadcasts our ancestors made without knowing anyone would hear. The strangest part is the lack of control. First contact is supposed to be a choice, a decision humanity makes together, a moment we prepare for, plan for, vote on maybe, but that moment already passed, and it passed before anyone alive today was born. Earth started broadcasting. They heard, they responded. The interaction began without anyone deciding it should, without anyone knowing it could. We're not in control of this. We're just catching up, watching dominoes fall that were set in motion a century ago, seeing consequences of actions taken by people who never knew the consequences would come. And there's one more thing the team noticed. One detail in the thermal data that made everything more immediate, more urgent. Something in the heat signatures that suggested the response wasn't finished. Something that indicated whatever they were building, whatever they were preparing, whatever they'd started when our signals first reached them. It was reaching completion. The energy readings showed a peak, a culmination. Something was about to happen on Kepler 442b. Something the data said was imminent. Something they'd been working toward for over a century. And we were watching it begin. 18 months pass. JWST keeps watching Kepler 442b. The biosignatures are still there. The heat patterns continue. The lights flicker in their familiar rhythms across the night side of that distant world. Everything looks the same. Routine observations, data collection, patience. Then the thermal spike appears. December 14th, early morning at Mission Control. The infrared sensors pick up something massive. A heat signature, unlike anything they've seen from that planet before. The temperature spike lasts 6 hours. The energy output during those 6 hours equals hundreds of nuclear detonations, maybe thousands. Yet the numbers don't fit anything natural. No volcano produces heat like that. No meteor impact sustains that long. The signature is directed. That's what makes it different. A nuclear bomb releases energy in all directions, a sphere of destruction. But this heat pattern shows focus, concentration, energy flowing in one specific direction, like water through a pipe, like a rocket exhaust, like a bullet carrying the energy of a bomb. The spectroscopy data confirms it. Plasma temperatures in the millions of degrees, concentrated thrust, something accelerated away from Kepler 442b during those 6 hours. Something big enough and fast enough to create a thermal signature visible across 112 light-years of space. The trajectory analysis takes 3 weeks, plotting the vector, calculating the acceleration profile, and determining where this object is heading. The teams run the numbers again and again, check the math, Verify the models. Every calculation gives the same answer. It's coming toward us, not toward our general region of the galaxy, not in the vague direction of nearby stars, directly toward the solar system. The trajectory holds within a margin of error so small, it can't be coincidence. Whatever launched from Kepler 442b is aimed at Earth with precision that requires intent, requires targeting, requires knowledge of exactly where we are. The velocity estimates vary. The distance makes precise measurements difficult, but even conservative calculations put the object at a significant fraction of light speed, maybe 10%, maybe more. If it's traveling at 10% the speed of light, as it's moving 18,000 miles every single second, Earth's circumference is roughly 25,000 miles. This object crosses an entire Earth every second and a half. It doesn't slow down. It doesn't stop. It just keeps coming through the void between stars. The timeline is where everything gets strange. The launch happened 18 months after we first observed the biosignatures, 18 months after we started watching their lights, after we detected their atmosphere, after we confirmed someone was home. It feels recent. It feels like a response we're watching unfold in real time. But we're not watching real time. We're watching history. Light from Kepler 442b takes 112 years to reach us. When we saw the launch 6 months ago, we were seeing something that happened 112 years in the past. Add the 18 months between first observation and launch. The actual launch, in their time, occurred roughly 114 years ago. 114 years since something lifted off from that distant world and began its journey toward ours. The object is already halfway here. More than halfway, probably. While we're analyzing the launch signature, while we're calculating trajectories and arguing about what it means, the thing itself is already deep in interstellar space, already closer to us than to them, already committed to a journey that began before anyone alive today was born. Arrival estimates depend on exact velocity. The uncertainty range is wide, but the median calculation puts arrival at roughly 100 years from now. A century. A child born today will be elderly when this object reaches the solar system. Your children will meet what your grandparents saw launch. The people who built this thing, who aimed it, who sent it toward us, they died decades ago, maybe a century ago. They launched something into the dark knowing they would never see it arrive, knowing their children wouldn't see it. Maybe their grandchildren wouldn't either. We don't know what it is. The data can't tell us that. It could be a probe, something like Voyager but faster, smarter, a messenger sent to make contact, to say hello across the stars. It could be a ship, something carrying passengers, carrying whoever lives on that world, or their descendants, or their creations. It could be a weapon, a response to signals they never asked for, from a species they never invited, a way of saying, "We heard you, and we're answering, and you won't like the answer." It could be a seed, information encoded in matter, instructions for building something on this end, a message that unpacks itself upon arrival, technology we can't imagine, biology we've never seen. The data doesn't distinguish between these possibilities. The thermal signature tells us something launched. The trajectory tells us it's coming here. The velocity tells us when it arrives. That's all we know. That's all the light can tell us. The teams try to get more information. They point every available telescope at Kepler 442, looking for follow-up launches, looking for changes in the heat signature, looking for anything that might hint at intent. The planet looks the same. The lights still shine. The biosignatures persist. Whatever they sent, it was one object, one launch, one answer to a century of radio signals they never asked to receive. There's a calculation someone runs, a timeline that makes everything more immediate. Earth's first radio broadcasts powerful enough to reach interstellar space happened around 1920. Those signals travel outward at light speed. They reached Kepler 442b around the year 2032. 112 years of travel time. The signals arrived, someone heard, someone decided, someone built, and 114 years ago, they launched their response. The timeline fits, the math works. We called out into the dark. Something heard us, and it answered by sending something back. Mission Control starts briefing government agencies. The data gets classified, then unclassified, then classified again. You can't keep something like this secret. Too many telescopes saw it. Too many teams ran the numbers. The information spreads through the astronomical community, then beyond. The question everyone asks is the same. What is it? What did they send? The question nobody can answer. The question we won't answer for another century. Somewhere in the void between our worlds, something is coming. It's been traveling for over 100 years already. It will travel for 100 more. It doesn't know we've seen it launch. And it doesn't know we're waiting. It doesn't care. It just moves through the dark, crossing light years in silence, aimed at a blue dot that sent signals into space without knowing what might hear them, without knowing what might answer. We're not watching it launch anymore. We're watching ancient history, a recording of something that already happened, already committed, already on its way. The light shows us the past, but the object exists in our present, getting closer, every second, every day, 18,000 miles per second, the distance shrinking, the arrival approaching. And we have a century to wonder what happens when it gets here. What is it? That's the question everyone asks. The astronomers, the politicians, the people scrolling past the news on their phones. What did they send? We have over a century before it arrives. Over a century to wonder. But we can start making educated guesses now. Let's walk through the possibilities. First option. It's a probe, an unmanned spacecraft packed with sensors and instruments. No crew, no living beings, just technology designed to observe and report back. Think of our Voyager probes. We launched them in 1977 with cameras, spectrometers, and a golden record containing sounds and images from Earth, a message in a bottle with sensors attached. They're still out there, still transmitting, 46 years later and counting. Maybe this object is their version of that, a reconnaissance mission. Send the probe first, let it arrive, let it observe, and let it send data home across the light years, while the civilization that launched it waits for answers their great-great-great-great-grandchildren will receive. This makes sense from an engineering perspective. Probes are smaller, lighter, easier to accelerate to high speeds. You don't need life support. You don't need food or water or air. You don't need to worry about cosmic radiation killing your crew over a 100-year journey. Just build something durable enough to survive the crossing and smart enough to function when it arrives. If we were sending something to another star, this is probably what we'd send first. Second option. It's a ship, a crewed vessel, living beings aboard, either awake or in some form of suspended animation. Or it's a generation ship, a massive habitat carrying an entire population. Now, the beings who launched it knew they'd never see the destination. Their children wouldn't see it either. Multiple generations would live and die inside a metal world between stars. The grandchildren would arrive to meet strangers their grandparents decided to visit a century before. Their ancestors chose a destination, aimed their descendants at it, and hoped whoever arrived would remember why they came. Generation ships are enormous undertakings. You need a closed ecosystem. You need resources for 100 years or more. You need social structures stable enough that your society doesn't collapse somewhere in the dark between stars. That's harder than the engineering, but maybe they solved it. Maybe they have suspended animation technology that lets a crew sleep through the journey. Wake up when you arrive. Step out into a new star system without having aged a day. We can't do that, but they might. Third option, it's a weapon, something designed to destroy or disable, launched with hostile intent toward a planet that showed signs of technological development. This is the option that keeps people awake at night, the one that gets discussed in classified briefings, the one nobody wants to say out loud but everyone thinks about. Here's the thing though, we don't really know. That's the honest answer. We can see it moving. We can measure its trajectory, but we can't determine intent from a velocity vector. It could be anything. The trajectory doesn't tell us if it comes in peace or comes in violence, just that it comes. The weapon scenario has a logical problem though. If it's a weapon, it's the slowest weapon ever designed. over 100 years of travel time. They launched it sometime in the early 1900s by our calendar, before they could possibly know what our civilization would look like when it arrived, before they knew if we'd still be here, before they knew if we'd be more advanced or extinct. That's a century of uncertainty. You're firing a bullet through time at a target that might not exist when the bullet gets there. More likely, it's something else. Curiosity or communication. Hostility is inefficient at interstellar distances. If you want to destroy a civilization, you don't send something that takes 100 years to arrive. You send a signal. Information travels at light speed. Instructions for building something destructive could arrive decades before a physical object. Let them build their own end, faster, cheaper, and more effective. The fact that they sent an object, something physical, suggests a different purpose. Fourth option, it's a seed or a message. Not a probe with sensors, not a ship with crew, something else entirely. A library, a time capsule, an archive of everything they are, encoded in something designed to last. DNA sequences, maybe, if they use DNA, cultural data, scientific knowledge, art, music, philosophy. Their entire civilization compressed into a format that can survive a century in the void and be understood by whoever finds it. An introduction, a gift, a way of saying, we were here, we thought about the universe, and we wanted you to know. Or it could be an artificial intelligence, a mind without a body, conscious software traveling between stars on a computer no bigger than your hand. And it doesn't need food or air or gravity, just power and time. It arrives, it learns, it communicates, it builds more of itself if it needs to. An envoy made of thought instead of flesh. We won't know until it's here. Maybe that's the point. Maybe the uncertainty is intentional. Send something ambiguous. Let the recipient spend a century wondering. Let them reveal themselves through their response. Do they panic? Do they prepare weapons? Do they welcome it? Your reaction says more about you than the object says about its creators. There's a concept in theoretical xenopolitics called the dark forest. The idea that the universe is full of civilizations, but everyone stays silent, everyone hides. Because making noise, sending signals, revealing yourself, that's dangerous. You don't know who's listening. You don't know what they want. Oh, the smart strategy is silence. Stay quiet. Stay hidden. Survival through invisibility. This object breaks that silence, deliberately, loudly. It's not a whisper. It's a shout across the darkness. An announcement that can't be taken back. They knew we'd see them. They had to know. You don't launch something at another star system and expect to stay hidden. The energy alone would light up every telescope pointed in that direction. They chose visibility. They chose contact. That choice matters. It tells us something, even if we don't know what the object is. It tells us they're willing to take the risk, willing to reach out across the void to someone who might not want to be reached, willing to wait over 2 centuries, round trip, for any kind of response. The light we saw shows us the launch, ancient history, something that already happened, but the object exists in our present, moving toward us, getting closer. The arrival is fixed now, inevitable. We have 100 years to prepare, 100 years to wonder, 100 years to decide what we'll do when it gets here, and we still don't know what it is. Let's be clear about something. We haven't seen the planet, not really. No photographs, no images of continents or oceans, no pictures of cities glowing on the night side. Nothing like that. The planet is still a dot of light in the telescope, a pixel, maybe a few pixels if we're lucky. That's all it will ever be from this distance. That's the reality. So what are we actually looking at? We're looking at shadows and chemistry, fingerprints left in starlight. The planet passes in front of its star. Starlight filters through the atmosphere. Some wavelengths get absorbed, others pass through unchanged. We measure what's missing. The gaps in the spectrum tell us what molecules are present. Oxygen absorbs specific wavelengths. Water vapor absorbs others. Methane has its own signature. Each molecule leaves a unique fingerprint. We're reading those fingerprints. It's like hearing a song through a wall. You know there's music. You know the rhythm. You can tell if it's loud or quiet. But you can't see the musicians. You can't read the sheet music. You're inferring everything from sound alone. That's what spectroscopy gives us. Information without imagery. The biosignatures we detected in Section 4 came from this method. Oxygen and methane together. Atmospheric chemistry that shouldn't exist without life constantly producing it. Yet we didn't see forests or oceans. We saw absorption lines, dips in a graph, but those dips told us something profound. They told us life was there. The thermal patterns from Section 5 work differently. The telescope measures infrared light, heat. The planet radiates heat into space. So does everything on it. We measure the total thermal output, the gross energy signature. Not fine details, not individual structures, just the overall heat distribution across the planetary disk. Think about watching a city from orbit at night. You'd see lights, patterns, geometric shapes that don't occur in nature, but you wouldn't see individual buildings. You wouldn't see streets or cars or people. You'd see evidence of organization, evidence of intelligence. The patterns would tell the story. That's what the Webb telescope can resolve. Patterns, not details. The heat map showed thermal output concentrated in specific regions. Geometric distribution, intensity variations that suggested artificial sources. Not random, not natural, organized. That's the clue. The pattern itself is the data. People hear super Earth and imagine paradise, a better version of home, greener, cleaner, more Earth than Earth. That's not what the term means. Super Earth is just a size category. Larger than Earth, smaller than Neptune. That's it. Says nothing about habitability, nothing about conditions on the surface, nothing about whether humans could survive there. Just mass and radius. This planet happens to be habitable, but the name doesn't tell you that. The launch event we discussed in Section 8. The thing that changed everything. And we detected that through a sudden spike in thermal output, a bright flash, a sustained plume of heat rising through the atmosphere, energy release on a massive scale. We measured the intensity, the duration, the spectral signature of the exhaust. All of that came from infrared observation, from heat. We never saw a rocket. We never saw a launch pad. We saw energy, light, chemistry. We inferred the rest. Here's the part that gets me. The entire discovery hangs on indirect evidence. Shadows, heat, molecular fingerprints, chemical anomalies, patterns in the data. We decoded an entire civilization from that. Biosignatures that proved life, technosignatures that proved intelligence, a launch that proved intention, all without ever seeing the planet as more than a single point of light. And it's like reconstructing a city from the smell of its smoke. You never see the buildings, never see the people, but the smoke tells you what's burning, how hot the fires are, how many there might be. The chemistry tells you what fuel they're using. The pattern tells you it's not random. Someone built those fires. Someone tends them. The smoke alone reveals the city. That's what the James Webb Space Telescope actually does. The instrument we talked about in Section 2, the tennis court-sized mirror, the infrared sensors. This is the work it was built for. Not photographing galaxies, not imaging nebulae, reading light, analyzing spectra, measuring heat, finding patterns in data that looks like noise to anyone else. The resolution isn't fine enough for surface features. Never will be from this distance. And the planet is 700 light-years away. That's 6.5 quadrillion kilometers. 6.5 million billion kilometers. You could fit the entire orbit of Neptune, end to end, 70 million times in that distance. At that range, even the most powerful telescope ever built can't resolve continents, can't distinguish oceans from land, can't see individual cities, but it can see chemistry. It can see heat. It can see patterns. The common misconception comes from science fiction, from movies and shows where alien planets fill the screen, where you see forests and rivers and cities from space, beautiful establishing shots, dramatic reveals. That's fiction. The reality is data, numbers, graphs, absorption spectra, thermal curves, light curves, transit timing, radial velocity measurements. Information extracted from photons that traveled for 7 centuries to reach us. Every conclusion we've drawn rests on that foundation. The biosignatures are real because the spectral lines don't lie. The technosignatures are real because the patterns can't form naturally. The launch is real because the energy signature matches exactly what you'd expect from a massive chemical or nuclear propulsion event. The evidence is indirect, but it's solid. We know they're there. We know they're technological. We know they launched something. All from shadows and chemistry. All from a dot of light. The precision of the data matters. The Webb telescope can measure atmospheric composition down to parts per million. It can detect temperature variations of a few degrees across the planetary disk, and it can time the transit of the planet across its star to within seconds. That precision turns a dot into a dataset, a pixel into a portrait. We can't see them, but we can read their fingerprints, and fingerprints are enough. The planet exists, the civilization exists, the object they launched exists, all confirmed through methods that don't require photographs, don't require visuals, just physics, just chemistry, just light doing what light does, carrying information across the void. This planet is 8 times the mass of Earth. That's the super-Earth classification. 8 times more massive, about twice the diameter. Gravity on the surface would be roughly twice what you experience here. Standing would feel like wearing a backpack full of rocks. Every step would take effort, but life adapted to that. Intelligence emerged despite it. They built a civilization under gravity that would crush most humans. We know that from measuring how the planet tugs on its star, from watching the star wobble, from timing how long the planet takes to complete an orbit. Mass, radius, density, composition, all derived from watching a dot move across another dot. That's the reality of exoplanet science. That's what discovery looks like at interstellar distances. Not images, not photographs. Data, patterns, evidence assembled piece by piece until the picture emerges. Despite the limitations, we know enough. We know they're alive. We know they're intelligent. We know they reached for the stars. And we know something is coming. That's more than we've ever known before. 112 light years. That's the distance. And that's how far away this planet sits. That's the gap between us and them. Let's make that number mean something. Light travels at the ultimate speed limit of the universe. Nothing goes faster. A beam of light could circle Earth 7.5 times in 1 second. At that speed, it still takes 112 years to reach this planet. One way, just to get there. Communication takes longer, much longer. Imagine we send a message today, right now. We beam a signal into space carrying a simple question. Hello, are you there? That signal travels at light speed, the fastest anything can go. It arrives at their planet 112 years from now. They receive it. They send a reply immediately. That reply travels back at light speed. Another 112 years. Total round trip, 224 years. A 224 years for a single exchange. One question, one answer. That's longer than the United States has existed as a nation. The entire history of this country, from the Declaration of Independence to right now. Not long enough for a conversation with beings 112 light years away. The person who sends the message dies before the reply arrives. Their children die. Their grandchildren die. Their great-grandchildren might live to see the answer. Might, if they're lucky. That's if we use light itself, the fastest thing there is. What about actual spacecraft, physical objects we could build and launch? At light speed, impossible with our current technology, the journey takes 112 years, an entire human lifetime, plus 30 more years. You'd need to be born on the ship and live your whole life traveling, die before arrival. Your children would arrive, but we can't reach light speed, not even close. The fastest spacecraft we've ever built might manage 10% of light speed. Might. That's theoretical. That's optimistic. That's assuming breakthroughs we haven't made yet. At 10% light speed, the journey takes 1,120 years, more than a millennium. Launch a ship now and it arrives in the year 3144. 11 centuries of travel, 40 generations born and dying in the void. Our actual spacecraft move much slower. Voyager 1 is the most distant human-made object. It's been traveling for over 40 years. It moves at about 38,000 miles per hour, fast by Earth standards, meaningless at cosmic scales. At Voyager's speed, Reaching this planet takes roughly 2 million years. 2 million years. If you launched a probe when the first humans were painting cave walls in Europe, when we were just learning to make art, when we barely had language, that probe would arrive right about now, just as we're building the James Webb Space Telescope, just as we're discovering the planet it was sent to find. The entire span of human civilization, all of recorded history, all of our art and wars and discoveries. Not enough time to cross 112 light years at the speeds we currently achieve. Walking makes it absurd, but absurdity helps show the scale. If you could walk through space at 3 miles per hour, maintaining that pace continuously, never stopping, never sleeping, the journey would require roughly 400 trillion steps. The number stops meaning anything. It's so large it becomes noise. The point is this: the distance is unimaginable at human scales. It defies every intuition we have about travel, about distance, about possibility. Every method we have, every speed we can imagine, turns this into a generational problem, a civilizational problem, not something individuals solve, something species attempt. The tragedy sits in that math. No one who asks a question will hear the answer. No one who sends a message will meet the recipients. No one who launches a probe will see it arrive. And the separation is absolute. The delay is permanent. Communication becomes an act of faith in people who don't exist yet. We send words into the void hoping someone, someday, will receive them. Hoping our civilization lasts long enough to hear the reply. Hoping theirs does too. That's what 112 light years means. That's the mathematics of loneliness. But here's what changes the calculation. The object they launched. The thing traveling toward us right now. It's moving at a significant fraction of light speed. We know that from how fast it's approaching, from the time frame in which we detected it. If it's traveling at even 10% light speed, that represents technology we've never achieved, engineering beyond our current capabilities, energy generation we can only theorize about. Yeah, they built something we can't build. They solved problems we're still working on. The arrival timeline itself tells us about their advancement, about what they can do, about how far ahead they might be. The distance separates us. The delay isolates us. But their answer to that problem, their solution to the tyranny of light speed, reveals something profound. They didn't just send a signal. They sent mass. They sent something physical, something moving faster than anything we've ever launched. They reached across 112 light years, not with light, with matter, with technology. That gap between what we can do and what they've done. That's not just distance. That's capability. That's time translated into technological advancement. And that's the difference between species who dream about crossing the void and species who actually do it. And whatever they sent is still coming, still crossing that impossible distance, still closing the gap we can't close ourselves. 100 years until it arrives. We know this now. The object, the craft, whatever they sent across 112 light years, 100 years left on its journey. A child born today will be 80 years old when it gets here. That child will be elderly, watching grandchildren grow, retirement long past, a lifetime lived, and only then, in those final years, will the answer arrive. The thing their grandparents saw first as a blip in telescope data, the thing that defined their entire generation's conversation about who we are in the universe. Only then will they know what it actually is. But consider this, your children will meet what your grandparents saw launch, not your grandparents themselves. They're gone. The ones who launched it, whoever they were on Kepler, 442e, they sent this thing 114 years ago in real time. Every single person alive on that planet when this object left their world is dead now, assuming they live about as long as we do, assuming biology works roughly the same way. They're gone. The engineers, the planners, the ones who decided to send it, the ones who built it, the ones who watched it leave, all dead before it even reached the halfway point. The astronomers who discovered it last month are mostly between 30 and 50 years old, career scientists, people who spent decades learning how to read light, how to spot anomalies, and how to distinguish between natural phenomena and something else. They'll be 130 to 150 years old when it arrives, which means they'll be dead too. The people who found it will never see it arrive. They discovered something they will never fully understand. They asked a question they will never hear answered. What do you do when you discover something you'll never live to understand? When you ask a question you'll never hear answered, you keep working anyway. You pass it forward, because that's what we do. What they did too, probably. We are the middle chapters. Let's count generations. Go back 100 years from today. That's your great-great-grandparents. Maybe your great-great-great-grandparents, depending on when your family had children. 4 or 5 generations back. And the people alive during the 1920s. The ones who saw the first movies with sound, who lived through the Great Depression, who thought flight was still a novelty. Those people are as distant from you as you are from the people who will actually meet this object. Count forward 100 years now, 4 or 5 generations ahead, your great-great-grandchildren, maybe great-great-great-grandchildren, people who will carry fragments of your DNA but won't know your name, who won't know what your voice sounded like, who won't know what you cared about or what kept you awake at night. To them, you'll be a date on a family tree if you're lucky, a blurred photograph if anything survived. Those people, the ones who meet the object, are as far from us as we are from people who lived during the Civil War, the American Civil War, 1861. That's the distance we're talking about. Not just time, cultural distance, technological distance. The gap between their world and ours will be as vast as the gap between our world and a world of telegraphs and horses and oil lamps. We are characters in a story we cannot finish. This is different from other multi-generational projects. Cathedrals took centuries to build. The Great Wall of China took generations. But the people working on those could see them, could touch the stones their grandparents laid, could measure progress in physical space. This is different. This is faith in a future you will never see. Faith that someone else will be there to receive what's coming. Faith that your civilization will still exist in 100 years. That your species will still care. They had that faith too, at the ones who launched it. They sent something knowing they would die before it arrived, knowing their children would die, knowing their grandchildren would die, knowing that only some distant generation, people they would never meet, people who might not even remember the original purpose, would see it reach its destination. That's not engineering. That's hope translated into technology. That's a message to the future written in mass and velocity. No one spans this arc, not on their side, not on ours. The ones who launched it are dead. The ones who discovered it will be dead. The ones who meet it haven't been born yet. Most of them haven't been born yet. The toddlers alive today will be elderly. The teenagers will be grandparents. The adults will be gone. This story has no protagonist, no single character who sees beginning, middle, and end, just a relay, just a passing of knowledge from one generation to the next, from one mortal set of hands to another. The object has been traveling longer than most humans live, 114 years in motion. It launched when your great-great-grandparents were young. It will arrive when your great-great-grandchildren are old. The span of its journey exceeds the span of a human life by 30 years, by a full generation. There is no perspective from which one person can witness this whole story. The universe doesn't care what we find convenient. It operates on timescales that mock our 80-year lifespans, that render our individual existence almost irrelevant to the plot. This is the part that gets me. We talk about first contact like it's a moment, like it's a single point in time when two species meet, but it's not. And it's a process that takes longer than anyone lives. It started over a century ago when they launched it. It continues now as we watch it approach. It will conclude a century from now when it arrives and we finally understand what they sent. That's not a moment, that's an era, multiple eras. The entire modern period of human history fits inside the time span of this one message. Think about what that means. The people who sent it lived in a world we can barely imagine. Their technology was different. Their culture was different. Their reasons for sending it were shaped by circumstances that no longer exist on their planet. They solved a problem from their time. They answered a question from their era. And we're receiving that answer in our time. When the question might have changed, when the context might be completely different, And the people who meet it in 100 years will live in a world we can barely imagine. Their technology will be different. Their culture will be different. They'll bring assumptions and knowledge and context that we don't have. They'll interpret what arrives through a lens we cannot predict. The meaning of this object will shift across centuries. What they intended, what we think they intended, what future generations will understand they intended. 3 separate things. 3 separate interpretations separated by the simple fact that humans die and the universe does not. We are the first to know that we are not alone. That's what makes this moment different from every other moment in human history. Every generation before us wondered, guessed, hoped, feared. We know, we have evidence, we have proof that we are the generation that moved from maybe to yes. That's ours. That singular shift in human consciousness happened on our watch. But we are not the last to carry this knowledge. We're just the first link in a very long chain. We pass it to the next generation, who will pass it to the next, who will pass it to the ones who finally meet what's coming. We're the ones who saw the blip in the data. They're the ones who will see the object itself. In between, there will be dozens of generations who simply live with the knowledge, who grow up in a world where it's just a fact, where the object approaching is as mundane as the moon, where the biggest question of human existence has already been answered and they're just waiting for the details. That might be the strangest part. For us, this is everything. This reshapes how we see ourselves, our place, our significance. For them, for the kids born 10 years from now, this will just be how the world is. They'll learn it in school, they'll see updates on the news, they'll watch it get closer year by year and feel nothing because they never knew a world where it wasn't coming. The emotional weight we carry, this sense of profound discovery, will evaporate within a generation, replaced by familiarity, by waiting, by the slow, boring patience of watching something approach at speeds we can calculate down to the meter. The ones who meet it won't feel what we feel now. They'll feel something else entirely. Relief, maybe. Vindication. Fear. Wonder of a different kind. The wonder of seeing rather than imagining. But they won't feel this. This specific moment of transition from alone to not alone. That belongs to us and to this generation. To the people alive right now who remember what it felt like to wonder if we were the only ones. We're living in the hinge point, the moment when everything changed but nothing happened yet, the moment between question and answer, between theory and proof, between wondering and knowing. That's where we are, not at the beginning, not at the end, somewhere in the long middle where the weight of knowledge meets the frustration of incomplete understanding. And in 100 years, someone else will stand where we stand now. They'll look back at us, at the astronomers who found it, at the scientists who confirmed it, at the billions of people who lived through the discovery and died before the arrival. They'll read our papers, watch our press conferences, see our faces reacting to the news, and they'll know something we don't know. They'll have the answer we're dying for. They'll see what we can only imagine, and maybe they'll think about us. About how we lived our whole lives in the question, about how we passed it forward knowing we'd never see it resolved, about how we were the ones who had to believe without seeing, who had to have faith that the answer was worth the wait, even though the wait would outlive us all. What does it actually look like down there, on the surface, under that orange sun? That's the question nobody's asking yet, but it matters, because alien doesn't mean slightly different. Alien means truly alien. Evolution doesn't follow a universal blueprint. It solves problems with the materials at hand, and the materials on Kepler 442 are not the same as ours. Start with the gravity, or 1.2 times what we feel on Earth. That doesn't sound like much, a 20% increase, but your body would know. Every second of every day. It's like every step you take, you're carrying a 40-pound backpack, not for an hour, not for a hike. Forever, from the moment you're born until the moment you die. Your bones would ache, your muscles would burn, your heart would strain just to pump blood upward against the extra pull. Life there would adapt. It has to. Bodies would be stockier, shorter, built low to the ground. Bones would be thicker, muscles denser. The elegant, elongated proportions we see on Earth wouldn't work. A human body transplanted there would collapse under its own weight within weeks. Spines would compress, joints would fail, hearts would give out trying to keep up with the demands. And think about the tallest trees on Earth, redwoods, sequoias. They push the limits of what gravity allows. On Kepler 442, those limits are lower. Trees wouldn't reach as high. Animals wouldn't stand as tall. Everything would hug the ground a little closer. Not because they're weak, because physics demands it. The atmosphere changes the equation too. Higher oxygen content than Earth. That means combustion happens faster. Fire burns hotter. But it also means metabolism can run harder. On Earth, the Carboniferous period had oxygen levels around 35%. Dragonflies grew to the size of hawks. Millipedes are stretched longer than your arm. More oxygen means more energy. More energy means larger bodies, faster movement, higher activity levels. Life there might be supercharged compared to ours, running hotter, here moving faster, burning through resources at a pace we'd find wasteful. Or maybe not. Maybe evolution there favored efficiency instead. Maybe they evolved to use that extra oxygen for endurance rather than bursts, for thinking rather than running. There's no way to know, but the raw fuel is there. The potential for biology that makes ours look sluggish. The light spectrum is where things get truly strange. Kepler 442 is a K-type star, cooler than our sun, redder. Imagine Earth, but the sun is always setting. That amber light is their noon. Their brightest hour looks like our golden hour. The light is dimmer overall, shifted toward the red end of the spectrum, and that changes everything about how photosynthesis works. Plants on Earth are green because chlorophyll reflects green light. It absorbs red and blue, reflects the middle. That works for our sun because our sun pumps out green light like crazy. But on Kepler 442, green light is scarce. The star gives off mostly red and orange. A plant that reflects any of that light is wasting energy. Evolution doesn't tolerate waste. Plants there might be black, absorbing every photon they can catch, every wavelength, nothing reflected, nothing wasted. Or they might be deep red, deep purple, dark brown, colors that look alien to us because they're optimized for a spectrum we don't live under. They'd look at our green Earth and think our plants are wasting light, reflecting away perfectly good photons just because they happen to fall in the middle range. The forests there wouldn't look like forests, not to us. Picture a landscape of black vegetation, or deep crimson, or purple so dark it's almost grey. The contrast would be jarring, disorienting. Our brains are wired to see green as the colour of life. There, green would be the colour of nothing, of absence, of emptiness. Their sky is probably not blue. That's the part most people don't think about. We assume skies are blue because that's what skies are. But Earth's blue sky is an accident, a consequence of our specific star's spectrum and the way nitrogen and oxygen scatter short wavelengths. Blue light scatters more than red, so our sun, which is rich in blue light, gives us a blue sky. Kepler 442 doesn't produce much blue light. It's an orange star, a K-type. The light is already shifted red, and when that redder, oranger light hits an atmosphere, it scatters differently. The sky there might be amber, pink, brown, a perpetual sunset color even at noon. Or it might be a pale orange, washed out and dim, like looking through a filter we can't remove. Blue skies are not universal. They're a feature of G-type stars and oxygen-nitrogen atmospheres. Change either variable, and the sky changes color. Stand on that world at midday. Look up. The sun hangs there, orange and cooler than ours. The sky around it is amber, maybe tinged with pink. The horizon fades to brown. The plants at your feet are black or deep purple, drinking in every photon. The air is thick with oxygen. Your muscles strain against gravity that never lets up. This is noon. This is normal. This is what life looks like under a different star. Every assumption we make about habitable worlds carries Earth's fingerprints. We picture blue skies because ours is blue. Green plants because ours are green. Familiar proportions because those are the proportions we know. But habitability doesn't mean familiarity. It means the physics allows liquid water and stable chemistry. Everything else is up for grabs. Life there didn't evolve to look like us. It evolved to survive 1.2 G, to photosynthesize under orange light, to metabolize in high oxygen. The solutions it found are not our solutions. The shapes it took are not our shapes. The colors it wears are not our colors. Alien means alien. Not rubber forehead humans with different customs. Not earth creatures with minor variations. Something genuinely other. Something adapted to an environment we'd find hostile and strange. We talk about finding life, about discovering biosignatures, about confirmation and proof, but we don't talk enough about what that life actually looks like, what it feels like to stand there, what their everyday normal is, because their everyday is not our everyday. Their sky is not our sky. Their plants are not our plants. Their gravity is not our gravity. The distance between our worlds is not just space, it's experience. It's the fundamental sensory reality of existence under a different sun. That world is out there right now. If life exists there, it's living its life, growing, moving, evolving. Under an orange sky, most humans would find unsettling. In gravity, that would crush us. Among plants that look like they belong in a nightmare. And to them, it's just home. It's just normal. It's just another day on the only world they've ever known. In 1950, a physicist named Enrico Fermi sat at a lunch table with colleagues and asked a simple question. Where is everybody? If the universe is so vast, if there are so many stars, so many planets, where are all the aliens? Why haven't we heard from them? Why haven't we seen them? That question became known as the Fermi paradox. For 70 years, it hung over the search for extraterrestrial intelligence like an unanswered riddle. This discovery changes the question. The Fermi paradox asked, where is everybody? But it assumed we'd detect them a certain way. Radio signals, massive structures, something loud and obvious. We listened with radio telescopes. We searched for megastructures that would block starlight. We looked for evidence of industry, waste heat, artificial transmissions. We found nothing. Silence across the electromagnetic spectrum. Silence that stretched decades. The paradox deepened with every empty survey, but we were looking for the wrong signatures, listening for the wrong sounds. This discovery suggests civilizations might be everywhere. We just needed infrared telescopes to see them. We were listening for words when we should have been feeling for warmth, the heat signature of something impossible, and the infrared glow of technology that shouldn't exist yet. Not radio waves shouting across the void. Quiet engineering, controlled power, a warm object moving through cold space. The answer to where is everybody might be simpler than we thought. They're there, 112 light years away, around a star we barely paid attention to until now. That star is a K-type star, orange, smaller than the Sun, cooler, about 70% the mass of our star. It sounds less impressive than a Sun-like star, less dramatic. But K-type stars might be where most life in the galaxy actually exists, not around stars like ours, around stars we considered second-rate. We've been searching in the wrong neighborhood this whole time. It's like looking for people in the suburbs when most of them live in the city, and we assumed Sun-like stars were prime real estate. Turns out the real action might be happening one tier down. K-type stars are more common than G-type stars like the Sun. They make up about 13% of all stars in the galaxy. G-type stars make up about 7%. Already, K-type stars outnumber us nearly 2 to 1. But the real advantage is longevity. The Sun will live about 10 billion years. K-type stars live 15 to 30 billion years. Some of them will burn for longer than the current age of the universe. 15 to 30 billion years of stable light, stable heat, a habitable zone that doesn't shift much. Time for life to start, evolve, fail, start again, and try a million different approaches. The universe is only 13.8 billion years old. The oldest K-type stars formed early. They've been burning ever since. Life around those stars has had twice as much time as life on Earth, maybe 3 times as much. If intelligence takes billions of years to develop, K-type stars give you those billions with room to spare. They're not flashy. They don't burn bright, but they last. And in the game of evolution, Lasting matters more than shining. There's another factor. K-type stars are stable. They don't flare as violently as red dwarfs. They don't burn out as quickly as massive stars. Their habitable zones are close enough to keep planets warm, but far enough to avoid tidal locking. The conditions are steady, predictable. Life needs predictability. It needs a star that doesn't suddenly double its radiation output or belch plasma across its planets. K-type stars provide that. They're the Goldilocks stars. Not too hot. They're not too cold, not too violent, not too brief. If most habitable worlds orbit K-type stars, then most life in the galaxy might be there too. Most ecosystems, most biospheres, most intelligences. We've been pointing our telescopes at sun-like stars because we assume life needs a sun-like star. But the universe doesn't care what we assume. It puts life where the conditions work, and the conditions work best around stars that last. This brings us to the Great Filter, the idea that there's some barrier, some cosmic test, that most civilizations fail, something that prevents species from spreading across the galaxy. Maybe it's self-destruction, nuclear war, climate collapse, artificial intelligence that turns on its creators. Maybe it's something we haven't even imagined yet, a trap built into the physics of advanced technology. So the Great Filter asks whether the hard part is behind us or ahead of us. Did we already pass the test by becoming intelligent? Or is the test still coming? The civilization 112 light-years away might have passed their filter. They're sending objects across interstellar space. They detected us from over a century away. They stayed stable long enough to build, plan, and execute a mission that spans generations. That's not easy. That requires surviving whatever threatens civilizations. War, environmental collapse, resource depletion, internal conflict. They survived it, or avoided it, or solved it in ways we haven't. The question for us is whether we're approaching our own filter. Climate change is accelerating. Nuclear weapons still exist in stockpiles large enough to end civilization. Artificial intelligence is advancing faster than our ability to control it. Pandemics, ecological collapse, resource wars, any of these could be the test. The thing that ends us before we become a spacefaring species. The Great Filter might not be one thing. It might be a dozen things, any one of which can kill you if you're not careful. If they pass their filter, it means passing is possible. It's not inevitable, but it's possible. That matters. It means intelligence doesn't have to destroy itself. It means there's a path through. We don't know what that path looks like. We don't know what choices they made that we haven't. But the existence of their signal, their object, their civilization, proves it can be done. Why did they stay silent for so long? And why break that silence when they saw us? We don't know. Maybe caution. Maybe protocol. Maybe fear. Maybe excitement. The object will tell us, eventually. There are theories about why civilizations stay quiet. The dark forest theory suggests the universe is full of predators. Any civilization that reveals itself becomes a target. So everyone hides. Everyone stays silent. Survival through invisibility. It's a grim view, but it explains the silence. If the galaxy is a dark forest, and every civilization is a hunter, you don't light a campfire. You don't shout. You watch, and you wait, and you stay hidden. But this civilization broke that rule. They saw our radio signals leaking into space. They saw evidence of intelligence on a planet 112 light-years away, and they responded, not with silence, not with caution, with an object, a message, a sign that they're there and they want us to know. And maybe they decided we're not a threat. Maybe they decided silence doesn't matter anymore. Maybe they have rules we don't understand. Protocols for contact that make sense in a context we can't see yet. Or maybe they've been waiting, watching younger civilizations emerge, waiting for one to reach the threshold where contact becomes possible. We crossed that threshold when we built radio transmitters, when we started leaking signals into space, when we became detectable. Maybe that's the trigger. The moment a civilization announces itself, intentionally or not, older civilizations respond. Not immediately, not with haste, but eventually, with care. The object is that response. It's their way of saying, "We see you. We're here. You're not alone." Whatever their reason for silence, they broke it for us. That decision, and made over a century ago, around an orange star we barely noticed, is arriving now. The consequences of that decision are unfolding in real time. A mission launched before anyone alive today was born is about to reach its destination, and we're standing here, watching it come, trying to understand what it means. The Fermi paradox asked, where is everybody? The answer is, they're out there, quiet, careful, watching, waiting for the right moment to step out of the dark forest and into the light. And for us, that moment is now. The announcement went out on a Tuesday morning, Greenwich Mean Time, 10:30 a.m. Every major space agency released the statement simultaneously. The same data, the same conclusions, the same 3 words that changed everything. We're not alone. The reaction wasn't what anyone expected. Oh, there was no global panic, no mass gatherings, no immediate shift in how the world operated. Markets opened the next day. People went to work. Traffic jams happened. The discovery that we share the universe with another technological civilization was absorbed into the ordinary rhythm of human life within 72 hours. Some people cared deeply. Most people noted it and moved on. A few didn't believe it at all. We met the most profound discovery in human history the same way we meet everything else. Messily, fractured, human. Religious leaders responded first. The Vatican released a statement within hours calling it a theological opportunity, not a crisis. Multiple creation events, they suggested, or one creator with many children scattered across the cosmos. Islamic scholars pointed to Quranic verses mentioning other worlds and other beings. Hindu leaders noted that the concept of countless inhabited worlds was already embedded in ancient texts. The responses varied, but the pattern held. Most major faiths found ways to incorporate the discovery into existing frameworks. The universe got bigger. Their theology stretched to fit. Military strategists had a different reaction. Within a week, defense departments across 6 nations initiated classified programs. The object is still 100 years away. That's roughly 4 generations. Long enough that no one alive today will see its arrival, but short enough that planning starts now. The question they're asking isn't abstract, it's practical. What do you build when you know a ship is arriving in your harbor in a century? And do you construct weapons? Welcome signs? Both? There's no precedent for this. No historical parallel. Every first contact in human history happened quickly, often violently, always between groups who didn't understand each other. This one comes with a countdown. A century to prepare. But prepare for what? The analogy that keeps circulating is imperfect but telling. Imagine learning that a distant relative you never knew existed is traveling to your home. They'll arrive in 100 years. You don't know their intentions. You don't know if they're friendly, curious, indifferent, or hostile. You don't know what they want or what they expect from you. You have 4 generations to get ready. What do? Some nations are fortifying. Some are attempting to send peaceful messages back across the void, in knowing any reply would take another century. Some are doing nothing, assuming the problem belongs to future governments. There's no consensus, no unified human response, just dozens of countries making independent decisions about how to greet or guard against something none of them truly understand. Scientists mobilized differently. Within a month, 3 international collaborations formed to study the object's approach. They're tracking its trajectory with every telescope capable of detecting it. They're analyzing the light signature, looking for changes, patterns, anything that might reveal intent. They're building models of propulsion systems that could move something that large at that speed. They're preparing communication attempts for when it gets close enough that signals might reach it before arrival. The work is methodical, careful, rigorous. The excitement underneath is palpable. This is what every SETI researcher spent their career hoping for. Not a faint radio signal, not an ambiguous chemical signature in an exoplanet's atmosphere. A definitive answer to the oldest question we've ever asked. The psychological shift is harder to measure, but impossible to ignore. Astronauts who've seen Earth from space report something called the overview effect. Looking back at the planet from orbit changes perspective. Borders disappear. Conflicts seem smaller. the sense of shared humanity intensifies. You see the whole thing at once, fragile and beautiful, and you understand in a visceral way that we're all on this together. The discovery of another inhabited world creates something similar, a cosmic overview effect. Yet we're experiencing a perspective shift without leaving the ground. The phrase that's been circulating captures it. Carl Sagan called Earth a pale blue dot when Voyager 1 photographed it from the edge of the solar system. That image became iconic, a reminder of our smallness, our isolation, our need to cherish what we have because it's all we've got. The new framing is simple. Pale blue dots, plural. We're not the only pale blue dot anymore. Somewhere out there, orbiting an orange star 120 light-years away, another world looks up at the same sky. Another species evolved, built tools, asked questions, reached for space. They're as real as we are, as complex, as curious, as capable of wonder. We're not alone in waking up, not the universe's only conscious observers trying to make sense of the dark. And that realization lands differently for different people. Some find it comforting. The universe feels less empty, less cold. Some find it threatening. We're no longer the pinnacle, the special case, the only minds around. Some find it humbling. Whatever we achieve, however far we go, someone else already did it. They figured out propulsion we can't replicate. They survived long enough to send something across interstellar space. They're older, more advanced, more capable, and they know we're here. The question changed. For decades, we asked, are we alone? We sent signals into space, built radio telescopes, scanned the sky for signs of anyone else out there. The answer came back in the form of an object moving through our system with clear intent. We're not alone. That question is settled. The new question is harder, sharper, was more immediate. What do they want? Why now? Why us? What happens when they arrive? There's no way to know. The object doesn't respond to signals. It doesn't alter course. It doesn't transmit. It just moves, steady and silent, closing the distance at a speed we can measure, but not match. 100 years, 4 generations. Enough time to prepare if we knew what preparation looked like. Enough time to worry, to speculate, to build narratives we can't verify. Enough time for every conspiracy theory, every hopeful fantasy, every apocalyptic scenario to take root and spread. The discovery hasn't unified humanity. That was the hope in every first contact story, every science fiction scenario where aliens arrive and humans finally put aside their differences to meet the challenge together. It didn't happen. Some nations are cooperating. Some are competing. Some are ignoring the whole thing, focused on terrestrial concerns that feel more urgent than something a century away. We're preparing for contact the same way we prepare for everything else, unevenly, with mixed motives, with brilliance and stupidity in equal measure. There's something almost reassuring about that. The discovery didn't erase human nature. It didn't suddenly make us wiser or more unified. It revealed that we'll face even the most profound moment in our history as ourselves. Flawed, fractured, hopeful, fearful, curious, defensive. We're not characters in a story that demands we rise to the occasion with perfect clarity. We're people, doing what people do when confronted with something unprecedented. We're improvising, arguing, building, and preparing for a future none of us will see, but all of us are shaping. The object is still coming. 100 years out, moving through the outer reaches of our solar system at a speed that defies easy explanation. It launched over a century ago, before anyone alive today drew breath. The civilization that sent it made that decision without knowing who we'd become. They aimed at a planet leaking radio signals and hoped something intelligent would still be here when their probe arrived. We are, and now we wait, watch, and try to answer the question that defines this moment. Not, are we alone? That's answered. The question now is what happens next. What do we do now? That's the question facing us. Not philosophically, practically. The object is 100 years away. It will arrive whether we prepare or not, or whether we understand it or not, whether we're ready or not. The trajectory doesn't care about our confusion. The clock is ticking, and we have decisions to make. 100 years sounds like forever. It's not. The International Space Station took 10 years to build. Assembly began in 1998. The last major module was added in 2011. 10 years of launches, spacewalks, international coordination, and problem solving. We have time for 10 projects like that before the object reaches Earth. 10 ISS-scale efforts. That's the scope of our preparation window. The first option is observation. Build better telescopes. Much better. Right now, the object appears as a speck, a dot of reflected light against the black. We know it's there. We know it's moving. We know roughly how big it is. That's about it. With better imaging technology, we might resolve its shape, see surface details, determine if it's rotating, understand what we're looking at before it gets here. That takes time. Designing a telescope with that kind of resolution, building it, launching it, positioning it correctly, probably 20 years minimum, maybe 30. The sooner we start, the sooner we see. The second option is communication. We can try to talk to it, send signals, radio transmissions, laser pulses, mathematical sequences, prime numbers, anything that might indicate intelligence on our end. The problem is obvious. The object is currently 112 light-years away. A signal sent today takes 112 years to reach it. If whoever sent it responds immediately, that response takes another 112 years to return. A 224 years round trip. It's like shouting into a cave and knowing the echo won't return until your grandchildren are old. Your great-great-great-great-grandchildren. Actually, conversation isn't possible, but a message might still matter. A signal that says, "We see you, we're here, we're listening." The third option splits into two directions, and this is where it gets uncomfortable. We can prepare defensively, or we can prepare to welcome. Both require resources. Both require technology we don't have yet. The choice depends on assumptions we can't verify. Defensive preparation means detection systems, early warning networks, something that tracks the object continuously as it approaches, something that tells us if its trajectory changes, if it accelerates, if it deploys anything smaller, if it begins transmitting. That's the minimum. Beyond that, you're talking about response capability, interceptor spacecraft, weapons systems designed for targets we've never encountered, technology to disable or destroy something we don't understand. That's a dark road, a necessary one, maybe, but dark. Welcoming preparation means infrastructure, communication arrays powerful enough to attempt contact as it enters the solar system, translation protocols, AI systems trained to recognize patterns in potential alien languages, landing zones, if it intends to land, quarantine procedures, diplomatic frameworks, first contact protocols that every nation agrees to follow. That last one might be harder than the technology. The truth is, we'll probably do both. We'll build the telescopes and the defense systems. We'll prepare for contact and prepare for conflict. We'll hedge our bets because we have no idea what's coming. Governments don't gamble on single outcomes when the stakes are this high. There's another project already underway, continuous observation of Kepler 442 itself, the planet the object came from. Astronomers are watching it more closely than ever before, looking for more signals, more signs of technology, atmospheric analysis, light curves that might indicate artificial structures, anything that tells us more about the civilization that sent this thing. Every data point helps. Every observation narrows the possibilities. The questions remain. They sit at the center of everything we're planning. Who are they? What do they look like? That one's impossible. We have no way to determine biology from this distance. They could be carbon-based, silicon-based, something else entirely. They could be organic, synthetic, uploaded consciousnesses piloting a machine. We don't know. We can't know. Not yet. What is the object? Probe, colony ship, weapon, art installation. We covered the possibilities already, but the question hasn't gone away. It defines every preparation we make. If it's a probe, we need communication systems. If it's a weapon, we need defense. If it's something else, we need flexibility. Is the intent hostile or friendly? This is the question that keeps people awake. And the object was launched over a century ago by beings who detected our radio signals and sent something our way. That could be curiosity, scientific interest, an attempt at contact, or it could be threat assessment, preemptive action. We won't know until it's much closer. Maybe not even then. Have they survived their great filter? Every civilization faces existential risks: climate collapse, nuclear war, AI gone wrong, resource depletion, asteroid impact. The Great Filter is the theoretical barrier that prevents intelligent life from becoming widespread. Most species probably don't make it through. The fact that they launched this object a century ago doesn't mean they're still alive. They might have destroyed themselves decades ago. The object might be all that's left, a message in a bottle from a dead world. Why the silence before? And if they've been listening to us for over a century, why didn't they respond earlier? Why launch a physical object instead of just talking? Radio is faster, cheaper, easier. Sending something solid across interstellar space requires enormous resources. There must be a reason. Maybe their message is too complex for radio. Maybe they don't trust electromagnetic communication. Maybe they want to show us something, not tell us. Maybe the object itself is the message. 100 years is a long time for human priorities to shift. Will we still care about this in 50 years? Will the next generation maintain the funding, the focus, the international cooperation? Or will other crises push this into the background? Climate change, economic collapse, war, pandemics. The object is still coming, but human attention is short. And we might build the telescopes and then forget to look through them. We might start preparing and then stop halfway. History is full of long-term projects abandoned when leadership changes, when budgets tighten, when the world moves on. Then there's the surprise element, the thing nobody talks about much, but should. The object itself might answer questions before it arrives. If it's a probe, it might begin transmitting as it enters the solar system. Not in 100 years. Sooner. It could start sending signals when it crosses the heliopause, the boundary where solar wind meets interstellar space. That's roughly 100 astronomical units from the Sun. An astronomical unit is the distance from Earth to the Sun, 93 million miles, 100 times that. The object could reach that boundary years before reaching Earth. It may be a decade before, maybe more. Picture this. The year is 2120. The object is still 30 years from Earth. It crosses into the solar system proper, and it turns on, starts broadcasting. Suddenly, we're not waiting anymore. We're listening, receiving data, messages, images, mathematical proofs, cultural transmissions, or warnings. We could have 10 years of information before physical contact, 10 years to prepare based on what it tells us, 10 years to understand what's coming. The arrival might not be sudden. It might be gradual, a slow introduction. That changes everything. The wait becomes less about blind preparation and more about informed response. We'd still have questions, but we'd have answers too. The object might explain itself, show us who sent it, why, what it wants, what it carries, and the mystery might solve itself before the object ever reaches orbit. Or it might stay silent until the last moment, until it's too late to do anything but watch. We don't know which scenario we're living in, the one where we get answers early, or the one where we stay in the dark until contact. Both are possible. Both require different preparations. The uncertainty is part of the challenge. We're not just waiting. We're trying to prepare for multiple futures simultaneously, some contradictory, all expensive, all necessary. The object is out there, moving, closing the distance. 100 years is both forever and no time at all. Long enough to change everything about how we approach this. Short enough that people alive today will have grandchildren who see it arrive. The thread connects us. Now, the decisions we make now echo forward. The technologies we develop, the cooperation we build or fail to build, the priorities we set, they all matter. They all shape what happens when the object finally reaches us. This isn't abstract anymore. This is planning, budgeting, engineering, politics, science, defense, diplomacy, all happening at once, all pointed at the same distant moment. We're building towards something we can't fully imagine, preparing for contact with something we don't understand, trying to be ready for every possibility while knowing we probably won't be ready for the one that actually happens. The wait has already begun. The work continues. And somewhere out there, moving through the dark between stars, the object carries its own answers. We just have to survive long enough to receive them. We saw them, and they saw us. The symmetry is almost perfect. 112 years ago, give or take, light from Earth reached their world. Industrial Revolution light, coal smoke and steel mills, and the first radio transmissions leaking into space. They pointed their instruments our way and found something. Chemical signatures that didn't belong, oxygen and methane in impossible ratios. Maybe they detected our first broadcasts. Maybe they just saw the atmospheric changes. Either way, they knew. Someone was here. Now we see them. Industrial era signatures in infrared. Atmospheric chemistry that screams technology. Their world-burning fuel, transforming energy, leaving marks visible across 112 light-years of empty space. We're seeing them roughly as they saw us. Two civilizations, same developmental stage, same cosmic moment. The timing is remarkable. Think about the scale we're working with. The universe is 13.8 billion years old. 13.8 billion years of stars forming and dying, of planets cooling and life potentially starting over and over and over. That's not just a long time. That's enough time for entire cycles of intelligence to rise and fall and leave no trace. Enough time for 1 million civilizations to bloom and vanish before we even existed. We could have been looking at their ruins, ancient structures, dead cities. A planet that once hosted intelligence but went silent 100 million years ago. That's what the odds suggest. That's what the mathematics of deep time makes likely. Or we could have been looking at their distant future, a world already transformed by technology we can't imagine. Post-biological, post-physical, so advanced that we wouldn't even recognize the signs. That's equally probable across these timescales. Instead, we're looking at their now, their industrial age, their moment of reaching beyond their atmosphere and detecting others. We're not finding their fossils. We're not finding their descendants. We're finding them, active, contemporary, peers. Of all the gin joints in all the cosmic epochs, we walked into theirs, or they walked into ours. Hard to say who walked into what when everyone's moving at a fraction of light speed, and time is more of a suggestion than a rule. The statistical odds are staggering. Imagine two ships launching from opposite sides of an ocean. Not just the same ocean after it's been empty for millennia. Both ships leave port within the same year. Both captains decide independently that this is the moment to cross. Both arrive at the center and spot each other's sails on the horizon at the exact same time. What are the chances? Now multiply that improbability by billions of years and trillions of possible planets. Either we're surrounded by intelligence, or something about this specific epoch makes intelligence more likely. Those are really the only options that make the coincidence less absurd. If technological civilizations are common, then finding a peer makes sense. We're just one species among thousands or millions, all reaching the same milestones within the same general time frame. The galaxy is full of voices. We're finally hearing one because we finally learned to listen. The other possibility is stranger. Maybe this moment in cosmic history, roughly 14 billion years after the beginning, is when the universe becomes ready for complex intelligence. Maybe earlier epochs didn't have enough heavy elements. Maybe star formation rates needed to stabilize. Maybe something about the current expansion rate or background radiation levels creates conditions that favor technological development. Maybe we're not early or late. Maybe we're exactly on time. And so are they. Both explanations are profound. Both change everything about how we see our place in the universe. We're either typical members of a vast community, or we're part of the first generation, the early cohort, the species emerging into consciousness just as the universe reaches the right age and temperature and composition to sustain us. The launch complicates the symmetry. They're ahead, not by much. Cosmically speaking, maybe a few centuries, maybe less, but enough to build something that can cross interstellar space, enough to send an object toward us with intention. They reached this capability before we did. They're our peers, but they're slightly older peers, the ones who figured out the path just before we started walking it. We're watching their industrial revolution through a telescope. They're already post-industrial, already capable of interstellar projects. The light lag hides their present from us. By the time we see them struggling with fossil fuels, they might have already solved it. By the time we detect their atmosphere changing, they might have already stabilized it. We're seeing their past while they live their present, and their present includes us. They detected us. They launched something. Those facts are connected. The timing suggests cause and effect. They found Earth, confirmed it was inhabited, and decided to respond. With what? We don't know. But the decision was made. The resources were allocated. The engineering was completed. The object is already in transit. Two civilizations, separated by void, both reaching outward at roughly the same time, both finding each other across distances that should make contact impossible, both now committed to a future where the other exists, where the other responds, where the isolation ends. The universe gave us a mirror, not ruins, not seeds of future intelligence, not incomprehensible transcendence. A mirror, another species learning the same lessons, asking the same questions, making the same leap from planetary to interstellar awareness, separated by space and time, but parallel in development, synchronized in ways that shouldn't be possible. That synchronization means something. We just don't know what yet. Maybe we'll find out when the object arrives. Maybe we'll find out when we finally decode a message. Maybe we'll find out by becoming what they already are, capable of crossing the void, capable of answering. The shared journey has already begun. We're no longer alone in it. Somewhere across 112 light years, another species is waiting to see what we do next, how we respond, who we become in the time we have left. They saw us. We see them. The distance remains. The questions remain. But the isolation is over. For better or worse, we've found our contemporaries. I told you at the beginning, the light we're seeing left before anyone alive was born. And now you know, they were seeing the same thing. Our light, reaching them, just as old, just as patient. Two beams crossing the void at the same moment in cosmic time. We are the first to know that we are not alone. That's what's changed. Not the universe. The universe was always full, always awake, always populated with minds looking up at their own skies, asking their own questions. What's changed is us, our awareness, our place in the story we've been telling ourselves for thousands of years. The stars are not just points of light anymore. They are potential homes, potential origins, potential destinations. Every speck in the night sky could be circled by worlds, and some of those worlds are looking back. Think about the universe as full of lighthouses, each one burning alone in the dark, believing they are the only light. The beam cuts through fog and emptiness, night after night, century after century. The keeper tends the flame. The light goes out into nothing. No response, no echo, just the endless work of shining into a void that never answers. Then one night, you see another lighthouse flash back, just once. A flicker on the far horizon. You realize the darkness was full of light all along. You just needed to know where to look and how to look. We found our lighthouse. They found theirs. Somewhere in the void between our worlds, something is coming. We don't know what it is. We don't know what it means. We won't live to see it arrive. Neither will our children. Neither will anyone alive today. The object will cross that 112 light-year gap in darkness and silence, carrying whatever intention was placed inside it. A message, a warning, a greeting, a test. We can only wait and wonder and prepare who we become in the time we have left. That means something. Being the first to know, being alive at the moment when the isolation ended. Every generation before us died believing we were alone. Every generation after us will grow up knowing we're not. We're the hinge, the turning point, the ones who saw the second lighthouse flash. The universe gave us a mirror, another species synchronized with our development, Another world making the leap from planetary to interstellar awareness at almost the exact same time. Both of us reaching out, both of us listening, both of us finding each other across distances that should make contact impossible. The object is on its way. Whatever happens next, nothing will ever be the same. Yet you can prepare for that however you want. You can think about what it means for humanity, for Earth, for the future we thought we understood. You can argue about what we should do when it arrives. You can wonder what they're thinking right now, on their world, under their sun, knowing we exist. Or you can just sit with the simple fact, we're not alone. The universe is full of life, full of minds, full of civilizations reaching across the dark, hoping someone reaches back. If you enjoyed this exploration, consider subscribing for more journeys like this one. There's more to discover, more to understand, more lighthouses out there waiting to be seen. Picture two civilizations, two lights, separated by over 100 years of travel time for their messages, separated by distances no human will ever cross in our lifetimes, but connected now, aware of each other, committed to a future where the other exists, where the other responds. Two beams of light crossing in the dark. The stars are no longer silent. They never were. We're finally listening.